What did classical physics get wrong? Classical physics could not explain why atoms were stable at all. It predicted that orbiting electrons around nucleus should radiate energy continuously and then spiral inwards and then collapse into nucleus. It also couldn't explain why atoms emitted only certain specific wavelengths of light. In this lecture, we'll talk about a Bohr's model and how Bohr actually followed those three key postulates. According to Bohr's atomic model, electrons and atoms follow three key postulates. The first postulate is electrons move in circular orbits, just like you see in this picture. And they do it under the influence of electrostatic attraction, much like planet orbiting the sun. That's why these electrons do not collapse to the nucleus, because they go around the nucleus under the influence of electrostatic attraction. The same reason why the planets do not collapse to the sun. The second postulate is not all orbits are allowed, only those for which electrons' angular momentum is quantized. This means electrons can only occupy certain discrete stable orbits with fixed energies. The third postulate is, while an electron remains in one of these all allowed orbitals, it does not lose or gain energy by radiation as long as they are in the same orbiter. Energy is only absorbed or emitted when these electrons jump from one orbit to another between these orbits, and the energy of emitted or absorbed photons equal the difference between these two levels, two orbits. So that energy is proportional to the difference in energy between two levels. That's called allowed. So these postulates together explain the discrete spectral lines of hydrogen by showing that only specific energy transmitted are possible, laying the foundation for modern quantum theory. What is angular momentum here? In Bohr's model, angular momentum refers to the momentum an electron has because it moves in a circular orbit around the nucleus, just like a planet orbiting the sun. So mathematically, it's given by this L is equal to mvr, where m is the electron's mass, v is its speed, and r is the radius of its orbit. So why did Bohr say angular momentum is quantized? Classical physics said electrons could have any orbit with any radius and any angular momentum, which would mean any energy. But if that were true, electrons orbiting the nucleus would constantly accelerate and should continuously radiate energy as electromagnetic wave. This would make them spiral into the nucleus quickly, and atoms would collapse into the nucleus, meaning that matter, as we know, it couldn't exist. But Bohr solved this by postulating that not all orbitals are allowed, just like here we wrote in this Bohr's orbits. They're not allowed. Not all orbits are allowed. Instead, the electron's angular momentum is quantized and it can only take on a specific discrete values. So the new angular momentum that Bohr said it's quantized, the equation is this. I apologize. It's not a h hat, so it's just a normal h divided by 2 pi. So where n is a positive integer, it can be 1, 2, 3, and h is Planck's constant. This rule restricts electrons to specific allowed orbits with fixed radii and energies. So again, why should angular momentum be quantized? The idea came from quantum principles emerging at that time, like Planck's quantization of energy in blackbody radiation and Einstein's photons in photoelectric effects. Bohr realized that if angular momentum were quantized, it would naturally explain the discrete energy level of the hydrogen atom and the line spectra observed experimentally. Electrons wouldn't lose energy continuously in the stable orbit. They would only emit or absorb energy when jumping between these levels, producing the specific spectral lines that matched Balmer's and Rydberg's formula perfectly. And the bottom line, Bohr's idea that angular momentum is quantized solved the failure of classical physics by explaining why atoms are stable and why they emit light in discrete spectral lines, laying the foundation for quantum theory. Electrons and atoms have quantized angular momentum.